Tonight, we're going to explore one of the strangest things the James Webb Space Telescope has ever found, and one of the most unsettling explanations anyone has ever proposed for it. We're going to talk about the little red dots. When Webb first opened its golden eye on the deep universe, it began sending back images of the cosmic dawn, the first few 100 million years after the Big Bang, a time no telescope had ever seen clearly before. And scattered across those images, by the thousands, were tiny smudges of deep red light, compact, round, impossibly small. At first they looked like nothing, faint specks among the great glowing galaxies. But as astronomers studied them, the little red dots became one of the deepest puzzles in modern cosmology, because no matter how the astronomers tried to explain them, the numbers refused to make sense. The red dots seem to be telling us that the early universe contained things that should not have been able to exist. For 3 years, the mystery only deepened. And then, just days ago, in the middle of June 2026, the James Webb Space Telescope returned a single spectrum, the most detailed measurement of one of these red dots ever taken, and it pointed to an answer so strange that astronomers had only ever discussed it as a theoretical curiosity. The answer is this: each little red dot may be a star, but not an ordinary star. A star with a black hole hidden inside it. A black hole sitting where the core should be, eating the star from the inside out, wrapped in a glowing shroud of gas that makes the whole thing shine deep red across 13 billion years of space. Tonight, we're going to find out whether that is true and what it would mean if it is. By the end of tonight, you're going to understand what the little red dots are, why they broke the standard picture of the early universe, and how a single object, magnified by a trick of gravity, may have finally cracked the case. You're going to understand what a black hole star actually is, how such an impossible-sounding object could form and survive, and why its discovery would solve one of the oldest and hardest problems in all of cosmology, the question of where the universe's monsters came from. And you're going to understand why, when the answer finally arrived, it was stranger and quieter and more beautiful than anyone watching had dared to expect. This is a journey into the first billion years of cosmic time, into a riddle written in red light, and into the heart of a star that should not be able to hold what it holds. There is no need to follow every number. There is no test at the end. The only thing tonight asks is that you let your body grow still while your mind drifts back to the cosmic dawn, where the answer has been waiting, hidden in plain sight since the universe was young. Before we begin, if you find that these slow journeys through the real universe help to quiet your mind at the end of the day, take a moment to subscribe so the next one can find you when you need it. If you are listening on Spotify, the follow button does the same quiet work, and it helps these long drifts through the dark reach more people than you would think. That is all. Settle in. Lower the lights. Let your breathing slow. Now, let's begin with the dots themselves, and with the moment astronomers realized that something in the early universe was very wrong. Let me set the scene properly, because to understand why the little red dots were such a shock, you have to understand what astronomers expected to see when Webb looked back at the cosmic dawn. The standard story of the early universe is a story of slow assembly. After the Big Bang, the cosmos was a smooth, dark sea of hydrogen and helium gas. Over the first few 100 million years, gravity gathered the gas into clumps. The clumps grew dense, and the first stars ignited, flooding the darkness with light for the first time. Those first stars gathered into the first small galaxies, and the small galaxies slowly merged and grew into large ones over billions of years. It is a gradual story, a story of small things forming first and big things forming later, patiently, step by step, brick by brick. When Webb looked back at the cosmic dawn, astronomers expected to see exactly this: small, faint, simple galaxies just beginning the long work of growing up. Now, let's begin with one more piece of the early universe that the red dots may touch, and it is one of the great events in all of cosmic history. a transformation that swept across the entire universe in its youth. Astronomers call it reionization, and the black hole stars may have played a part in it. Here is the story. After the Big Bang, once the universe had cooled enough, its hydrogen settled into a neutral state. Electrons bound quietly to protons, the gas dark and transparent to some light, but opaque to other kinds. For a stretch of time, the universe was a dark, neutral fog. Then, as the first stars and the first feeding black holes switched on, they flooded the cosmos with intense radiation, and that radiation began to strip the electrons back off the hydrogen atoms, ionizing the gas all over again across the entire universe. This great sweeping change, from neutral fog to ionized transparency, is reionization, and it marks the moment the universe became fully lit, the cosmic fog burning away as the first sources of light did their work. It is one of the major turning points in the history of everything, the end of the cosmic dark ages. For a long time, astronomers have debated what powered reionization. The obvious candidates were the first galaxies, full of hot young stars pouring out ionizing radiation. But there has always been a question of whether the stars alone produced enough, and whether feeding black holes might have contributed too, adding their own fierce radiation to the effort. And this is where the red dots become interesting, because if the cosmic dawn was sprinkled with thousands of black hole stars, each one a feeding black hole pouring out radiation, then they represent a population of light sources that might have helped drive the great reionization, helping to burn away the neutral fog and switch on the transparent universe we live in today. The details here are genuinely uncertain, and honest astronomers will tell you so. The black hole stars are wrapped in dense envelopes that absorb much of their radiation, which might mean they contributed less to reionization than a naked black hole would, keeping their fierce light bottled up inside their cocoons. Or the balance might work out differently, with enough radiation escaping to matter. This is exactly the kind of question the ongoing work will sort out, measuring how much ionizing light actually escaped from these objects, and weighing their contribution against the first galaxies. It is unresolved. But the very fact that the red dots are now part of the reionization conversation shows how central they have become to our picture of the early universe. Pattern interrupt. What is striking is how everything connects. The same little red dots that solve the seed problem, that explain the universe-breaking galaxies, that may be the ancestors of every central black hole, also turn out to be possible contributors to the great lighting up of the cosmos. They sit at a crossroads of early universe physics, touching one major question after another, a single strange population that keeps appearing in the answer to puzzle after puzzle. That is often a sign in science, that you have found something genuinely important, when the same object keeps turning up in the solution to problems that seemed unrelated. No one expects a single population of objects to touch so many of the great questions of the early universe at once. The seeds, the giants, the broken galaxies, the lighting of the cosmos. But the red dots do exactly that. No one predicts that solving the mystery of 1,000 crimson specks would ripple outward into so many other corners of cosmology. And absolutely no one anticipates how interconnected the early universe turns out to be. How one strange answer, a star with a black hole hidden inside it, sends light into so many of the dark rooms we have been trying to map. That is not entirely what they found. Among the expected faint young galaxies, Webb found the red dots. And the red dots did not fit the story at all. They were too compact, too red, and when astronomers tried to work out what they were made of, every answer led to a contradiction. If the red light came from stars, there were far too many stars packed into far too small a space, far too early in cosmic history, more stars than the young universe should have been able to assemble. The red dots looked, by the standard story, impossible, and there were not just a few of them. There were thousands. Whatever they were a common feature of the early universe, an entire population of objects that the textbook had no room for. Tonight, we're going to slow down on how the little red dots were discovered, because the story is recent enough that many people listening tonight were already alive and paying attention when it happened, and it shows how quickly a mystery can rise out of nowhere. The James Webb Space Telescope launched at the very end of 2021 and began its science observations in the summer of 2022. Almost immediately it began doing the thing it was built to do, peering deeper into the early universe than any telescope before it, using its enormous mirror and its infrared eyes to catch light that had been travelling toward us for more than 13 billion years, stretched so far toward the red by the expansion of the universe that only an infrared telescope could see it at all. The earliest deep surveys, with names like Sears and others, were meant to find the first galaxies, and they did. But almost as a side effect, they also turned up something nobody had gone looking for. In those first deep images, researchers kept noticing the same odd thing: small, intensely red, remarkably compact sources, far more compact than a normal galaxy should appear. At first they were curiosities, mentioned in passing. But as more fields were surveyed and the count grew, it became clear that these objects were everywhere in the early universe, a genuine population, not a handful of oddities. By 2023 and into 2024, the little red dots had a name and a reputation, and they had become one of the hottest and most argued about topics in all of astronomy. Conferences devoted sessions to them. Papers piled up. Everyone had a theory, and no theory quite worked. What made them so maddening was precisely their consistency. If they had been a random mess of different objects, that would have been easy to dismiss. But they shared a characteristic look, compact, deeply red, with a particular shape to their light, the same strange signature appearing again and again across the sky. That consistency meant they were a real class of object, one thing, repeated thousands of times, demanding a single explanation. And the single explanation refused to appear. For 3 years, the little red dot sat at the centre of the field like a splinter no one could remove, a 1,000-fold mystery that arrived with Webb and would not leave. No one expects a brand new telescope to immediately discover an entire population of objects that nobody predicted and nobody can explain. But that is exactly what Webb did within months of opening its eye. No one predicts that the cosmic dawn, the gentle era of the first faint galaxies, would turn out to be sprinkled with thousands of identical little crimson riddles, and absolutely no one anticipates how fast the mystery would grow, from a few odd specks in 2022 to one of the defining puzzles of modern cosmology by 2024, the question every early universe astronomer was suddenly trying to answer. No one expects the universe to hand them 1,000 impossible things at once, but that is essentially what Webb did. No one predicts, on first looking back at the gentle cosmic dawn, that it would be littered with compact red objects that refuse every ordinary explanation. And absolutely no one anticipates that the answer, when it finally came, would not be a new kind of galaxy at all, but a new kind of star, with the darkest thing in the universe beating where its heart should be. So that is where we begin. Thousands of red dots, scattered across the first billion years, each one a small contradiction, each one a quiet insistence that something about our picture of the early universe was incomplete. To solve them, astronomers first had to rule out what they were not. And that process of elimination, that careful closing of doors, is where the real story starts. None of this would exist without the telescope that found it, and it is worth pausing to appreciate why the James Webb Space Telescope, and only Webb, could have opened this particular door. The deep problem with seeing the early universe is that its light arrives in the wrong colour. When stars and galaxies in the cosmic dawn shone, they shone largely in ordinary and ultraviolet light, the same kinds of light familiar from nearby stars. But that light has been travelling toward us for more than 13 billion years, and across all that time the expansion of the universe has stretched it, shifting it toward longer and longer wavelengths, out of the visible range entirely and deep into the infrared. By the time the light of the cosmic dawn reaches us, it is no longer visible light at all. It is infrared, the light of heat. And to see infrared light from the faintest, most distant objects, you need a very large telescope, kept very cold and placed far from the warmth of the Earth, because a warm telescope glows in infrared and blinds itself. This is exactly what Webb was built to be. Its primary mirror is over 21 feet across, far larger than Hubble's, made of 18 gold-coated segments that gather faint infrared light with tremendous sensitivity. It sits not in low orbit, but about 1 million miles from Earth, in the cold and dark, shielded from the Sun, the Earth, and the Moon by a tennis court-sized sunshield that keeps its instruments chilled to hundreds of degrees below zero. Everything about it is designed to see the faint heat light of the early universe, without being drowned out by any warmth of its own. It is, in a real sense, a machine built specifically to look back at the cosmic dawn, and that is why the little red dots are a Webb discovery and could not have been anything else. They are faint, they are distant, and their light reaches us deep in the infrared, precisely the regime where Hubble and ground-based telescopes struggle and Webb excels. The red dots were always there, scattered across the early universe, their ancient light streaming past the Earth for as long as there has been an Earth. We simply had no eye that could see them clearly until Webb opened. The moment it did, the dots appeared in their thousands, and the mystery began. The telescope did not just find the answer. It found the question too, conjuring an entire population of objects into view that no previous instrument could have resolved. There is a particular instrument aboard Webb that did the crucial work here, called NIRS-SPEC, the Near-Infrared Spectrograph. It is the tool that takes the faint infrared light of a distant object and spreads it into a detailed spectrum, the 40 lines of glimpse 1775 among them. An image tells you an object is there. A spectrum tells you what it is. NIRS-SPEC is what turned the red dots from smudges into stories, and it is what read, in the fine structure of one magnified dot, the signature of a black hole hidden inside a glowing shell. No one expects that seeing the beginning of the universe would require a gold mirror the size of a house, chilled to hundreds of degrees below zero, 1 million miles from home, but that is what it took. No one predicts that an entire population of objects could stream past the Earth unseen for billions of years, waiting only for an eye sharp enough and cold enough to catch them. And absolutely no one anticipates how much was hiding just below the threshold of our old instruments, how the cosmic dawn was full of red riddles all along, invisible only because we had not yet built the machine that could see them. When astronomers first confronted the little red dots, there were 2 obvious explanations. 2 doors a researcher could walk through, and for a while the whole field argued about which one was right. Walk with me through the first door. Behind it, the red dots are galaxies, ordinary in kind if not in degree, vast collections of stars. The redness in this picture comes partly from distance, because the expansion of the universe stretches the light of faraway objects toward the red, and partly from dust, because galaxies full of young stars are also full of dust, and dust reddens light just as it does at sunset on Earth. Behind the first door, a red dot is simply a very distant, very dusty, very crowded young galaxy, an enormous swarm of stars assembled astonishingly early. By the end of tonight, you're going to understand why this took so long, and about the explanation that competed hardest with the black hole star, because the redness of the red dots was, for a long time, the very thing that pointed researchers in the wrong direction. Red light in astronomy usually has 2 ordinary causes, and both seem to apply to the red dots. The first is distance. The expansion of the universe stretches the light of faraway objects toward longer, redder wavelengths, so the most distant things appear reddened simply by how far their light has travelled. The red dots are very distant, so some of their redness is just this cosmic stretching, expected and uninteresting. The second cause is dust. Clouds of fine dust within a galaxy absorb blue light more than red, so light passing through dust comes out redder, the same reason the sun looks red through smoke or low on a hazy horizon. A galaxy full of dust looks red, and young, busy star-forming galaxies are full of dust. So for a long time, the natural reading of a little red dot was a distant, dusty, star-forming galaxy. Its redness explained by distance and dust together, its compactness just a sign of an early, not yet spread-out galaxy. This was the comfortable interpretation, the one that did not require any new physics, and many careful astronomers held it. The trouble was that it kept not quite working. Expectation. Dust alone could explain the red dots. Reality. To make the numbers fit, the dusty galaxy picture often required those impossible quantities of stars we discussed, packed too densely, formed too fast. The dust could explain the colour, but it could not by itself escape the arithmetic crisis. The redness was accounted for while the impossibility remained. The black hole star reframes the redness entirely. In this picture, the red dots are still reddened by distance, yes, but the deeper redness comes not from dust spread through a galaxy, but from the dense envelope of gas wrapped tightly around the central black hole. That envelope absorbs and reprocesses the black hole's fierce light, and what emerges is reddened, reshaped, the spectrum of a black hole seen through its own thick shroud. The redness is not a galaxy seen through a haze, it is a black hole seen through its own cocoon. Same colour, completely different cause, and the new cause carries no arithmetic crisis, because the light was never the combined glow of impossibly many stars. Pattern interrupt. This is a good example of how a single observed feature, in this case redness, can be consistent with very different underlying realities, and how only deeper data can decide between them. For years the redness was read as dust, and that reading shaped the whole debate, pushing people toward the galaxy interpretation and its impossible star counts. The detailed spectrum of glimpse and 77775 was what finally allowed astronomers to look past the simple fact of redness and read the finer structure underneath, the iron forest, the gas-made features, the buried black hole. The colour alone had been ambiguous all along. It took the fine print to settle what the colour actually meant. No one expects the most obvious feature of an object, its colour, to be the very thing that misleads you about its nature. But that is what happened with the red dots. No one predicts that the same redness could mean a dusty galaxy, or a black hole in a cocoon, two completely different things wearing the same shade. And absolutely no one anticipates how much patience it takes to get past the obvious reading of an obvious feature, to gather enough light to see that the colour you thought you understood was hiding something far stranger underneath. The trouble with the first door is the arithmetic, and the arithmetic is brutal. If the red dots are galaxies made of stars, then to produce that much red light from such a tiny patch of sky, they would have to contain a staggering number of stars, hundreds of billions of suns worth, sometimes more, packed into a region a small fraction of the size of our own Milky Way, and assembled within the first few 100 million years after the Big Bang. That is far more, far faster, far denser than the standard story of slow galactic assembly allows. The first door, taken seriously, does not just bend the textbook, it breaks it. It demands galaxies so massive, so early, that some astronomers began to wonder whether the entire model of how the universe grew its structure was wrong. These were the objects that earned headlines about web-breaking cosmology. If the red dots are stars, the universe assembled its giants impossibly fast. So astronomers looked at the second door. Behind it, the red dots are not made of stars at all, or not mostly. Behind the second door, each red dot is powered by a black hole. Not a quiet, sleeping black hole, but a feeding one, a black hole pulling in gas, the gas swirling and heating and blazing as it falls, lighting up the whole region. Astronomers call a feeding black hole like this an active galactic nucleus, and the brightest of them, quasars, are among the most luminous objects in the universe. Behind the second door, The red light is the glow of matter screaming as it falls toward a black hole, reddened and wrapped in gas rather than the combined light of impossibly many stars. The second door solves the arithmetic problem. A single feeding black hole can produce a tremendous amount of light from a tiny region, far more efficiently than stars, so you do not need an impossible number of suns to explain the brightness. But the second door opens a new problem in place of the old one. The light from a feeding black hole usually carries certain unmistakable signatures: the violent, fast motion of gas whirling close to the black hole, and a glow in X-rays from the superheated matter. And when astronomers looked for those signatures in the red dots, they often could not find them, or not clearly. The red dots did not look quite like ordinary quasars either. They were strangely quiet in X-rays. Their light did not show all the violence a feeding black hole should produce. So the second door too refused to close cleanly. Pattern interrupt. Here is where the mystery truly sharpened, because the red dots seemed to fail both tests at once. They were too bright and compact to be ordinary galaxies of stars which ruled against the first door. But they lacked the clear violent signatures of ordinary feeding black holes which ruled against the second door. They were caught between two explanations, fitting neither: an entire population of thousands of objects sitting in the gap between the only two answers anyone had. Expectation. Every strange new object is eventually sorted into one of the categories we already have. Reality. The little red dots stubbornly refused both categories, and the longer astronomers looked, the more it seemed that the universe was holding open a third door, one that no one had seriously walked through in a very long time. No one expects an object to fail every available explanation at once, but the red dots did exactly that for 3 years. No one predicts that 1,000 of the same kind of impossible thing would appear in the early universe and refuse to be sorted. And absolutely no one anticipates that the resolution would require reviving an idea so strange that, for decades, it had lived only in the margins of theoretical physics, an idea about a star that is not really a star at all. Because there was a third door. It had been sketched decades earlier by theorists thinking about how the universe might have built its first black holes. And behind that third door was an object that, if it existed, would look exactly like a little red dot, neither a pure galaxy of stars nor a naked feeding black hole, but something in between, something hybrid, something that had never been confirmed to exist. To understand it, we have to leave the red dots for a moment and go back to a question even older and even harder, the question that has haunted black hole astronomy for half a century. The question is this: where did the universe's giant black holes come from, and how did they get so big so fast? At the centre of nearly every large galaxy, our own included, sits a supermassive black hole, a monster millions or billions of times the mass of the Sun. We have spent decades studying them, and for the nearby ones in the modern universe, we have a reasonable story of how they grew slowly over billions of years, swallowing gas and stars and merging with other black holes. Given enough time, a small black hole can become a giant. The key phrase is, enough time. But the early universe did not have enough time. When Webb and other telescopes look back to the cosmic dawn, they find supermassive black holes that are already enormous, already billions of times the mass of the Sun, existing when the universe was only a few 100 million years old. And that is a genuine paradox, because there simply was not enough time for them to grow that big by ordinary feeding. Imagine finding a full-grown adult in a room you know was empty an hour ago. Either they grew impossibly fast, or they did not start from nothing. The early supermassive black holes are exactly that puzzle. They are too big, too soon. Something must have given them a head start. Let us go deeper into the seed problem itself, because it is the great open wound in our understanding of black holes, and the black hole star is, above all, an attempt to heal it. Tonight, we're going to lay the problem out as starkly as it deserves, because only then does the solution feel as satisfying as it is. The supermassive black holes we find in the early universe are genuinely, almost offensively too big. Consider the scale of the difficulty. Some of these early giants weigh 1 billion times the mass of the Sun, and we find them existing when the universe was only 700 or 800 million years old. Now, a black hole grows by feeding, and as we have discussed, there is a maximum rate at which it can feed, set by the Eddington limit. If you start with an ordinary seed, the kind of black hole left behind when one of the first massive stars dies, weighing perhaps 100 times the Sun, and you let it feed at the absolute maximum rate, without a single pause, for the entire available time, you still cannot reach 1 billion solar masses. The arithmetic simply does not close. The seed is too small, and the clock runs out. There is not enough time. To really understand why a black hole star is such a clever solution, we need to understand the speed limit it gets around, a fundamental rule of physics called the Eddington limit. It is one of those deep principles that governs both ordinary stars and feeding black holes, and once you grasp it, the whole picture sharpens. Here is the idea. Anything that shines also pushes. Light carries a tiny pressure, and when light streams outward from a bright source, it presses on any matter in its path, shoving it away. For most things, this pressure is far too gentle to notice. But when a source becomes extraordinarily luminous, the outward push of its own light becomes a serious force, strong enough to fight against gravity itself. The Eddington limit is the point of balance, the brightness at which the outward push of light exactly equals the inward pull of gravity. Shine any brighter than that, and your own radiation begins to blow your surroundings away. For an ordinary star, the Eddington limit sets a cap on how massive a star can be. Pile up too much mass, and the star's core burns so fiercely that its own light pressure blows off the outer layers, preventing it from growing any larger. This is why, in the modern universe, stars rarely exceed roughly a couple hundred times the mass of the Sun. The Eddington limit polices them. It is the reason there are no 1,000 solar mass ordinary stars wandering around today. For a feeding black hole, the Eddington limit does something similar and just as important. As a black hole pulls in gas, the gas heats up and blazes, and if the black hole tries to eat too fast, the radiation from all that infalling heating gas becomes so intense that it pushes the rest of the gas away, choking off the meal. The black hole, in effect, is held back by its own brilliance. It cannot eat faster than the Eddington limit allows, which sets a maximum growth rate. And that maximum growth rate is exactly the problem at the heart of the seed problem, because even eating at full speed, a small black hole seed cannot grow into a billion solar mass giant in the few 100 million years the early universe allowed. The speed limit is too slow. Now you can see what makes the black hole star so powerful. The dense envelope of gas wrapped around the central black hole changes the game entirely. The radiation from the feeding black hole, instead of escaping and blowing the gas away, gets trapped, absorbed and held by the thick surrounding envelope. The black hole can keep eating, sheltered, even though it is shining ferociously, because its light cannot escape to drive the food away. In a sense, the black hole star lets the black hole break past its own speed limit, feeding faster and more steadily than a naked black hole ever could, precisely because it is buried inside the very gas it is consuming. The envelope is both the food and the shield. No one expects a black hole's own brilliance to be the thing holding back its growth, but that is exactly what the Eddington limit means, a monster restrained by its own light. No one predicts that the way to grow a black hole fast would be to bury it inside a thick shell that traps that light and lets it eat in the dark. And absolutely no one anticipates how elegantly the black hole star turns the limit on its head, taking the very radiation that should choke the black hole's growth and using the surrounding envelope to smother it, so the monster can feed in peace. This is not a small discrepancy that better measurements might erase. It is a large structural gap between what the simplest theory allows and what the telescopes actually see. And it has only grown sharper with Webb, which keeps finding more of these early giants, and finding them earlier, pushing the problem harder. The universe built monsters faster than our straightforward picture permits. something is missing from the story. There are really only a few ways out, and they all involve giving the black hole a head start, a heavy seed. One way is direct collapse, the idea that a huge, pristine gas cloud falls together all at once into a massive black hole seed, skipping the ordinary stellar phase entirely, starting at tens or hundreds of thousands of solar masses instead of 100. Another way involves the black hole feeding faster than the Eddington limit normally allows, in bursts under special conditions, and the black hole star beautifully combines both of these advantages into a single object. It begins with a heavy seed, formed from the collapse of a massive cloud, and then it shelters that seed inside a dense envelope that lets it feed at or beyond the normal speed limit, growing fast and growing protected. It is a head start and a speed boost together, wrapped in one glowing package. This is why the possible confirmation of black hole stars is such a big deal, far beyond just explaining the red dots. If black hole stars were common in the early universe, and the thousands of red dots suggest they were, then the universe had a ready and abundant mechanism for manufacturing heavy black hole seeds and growing them fast. The seed problem, which has nagged at black hole astronomy for decades, would have its answer. The early giants would no longer be impossible. They would be the natural endpoints of a process the universe was running everywhere, in thousands of little red cradles at the cosmic dawn. The thing that looked like a crisis in our understanding would become the very evidence that resolves an older crisis. No one expects the universe's most troubling objects, the impossibly early giant black holes, to find their explanation in another set of troubling objects, the little red dots, but that is the shape of it. No one predicts that two separate crises, the red dots and the seed problem, would turn out to be a single problem with a single answer. And absolutely no one anticipates how often this is how science moves forward. Two stubborn mysteries sitting unsolved for years, until someone realizes they are not two mysteries at all, but one, seen from two different angles, waiting for the idea that joins them. Astronomers call that head start the seed problem. A black hole has to start from some seed, some initial object that then grows. And the question is, what were the seeds? If the seeds were ordinary, small black holes left behind by the deaths of the first stars, weighing perhaps 100 times the Sun, then there is no way to grow them into billion solar mass giants in the available time. The growth is capped. There is a speed limit on how fast a black hole can eat, and at that limit, a small seed simply cannot catch up to what we observe. So the small seeds do not work. The early giants demand something heavier to begin with, a head start measured not in hundreds of solar masses, but in tens of thousands, or hundreds of thousands. Before we get started to understand how a black hole star could form at all, we need to understand the world it formed in, and that world, the universe of the cosmic dawn, was profoundly unlike the one we know. It was a place where the rules of star formation themselves were different, and that difference is what made these strange objects possible. Go back to the first few 100 million years after the Big Bang. The universe then contained essentially only two ingredients, hydrogen and helium, the light elements forged in the first minutes of creation. None of the heavier elements existed yet. No carbon, no oxygen, no iron, no nitrogen, none of the rich chemistry that fills the modern cosmos and makes up the Earth and your own body. All of that would be manufactured later, inside stars and scattered by their deaths. But at the cosmic dawn, the gas was pristine, chemically simple, almost untouched. Astronomers call this primordial gas, and its purity changes everything about how it behaves. Here is why it matters. When a gas cloud collapses to form stars, it has to cool as it contracts, shedding heat so it can keep falling inward and fragmenting into star-sized pieces. In the modern universe, heavy elements and dust are extraordinarily good at this cooling, radiating heat away efficiently, which lets clouds fragment readily into many ordinary stars. But pristine gas, lacking those heavy elements, cools poorly. It cannot easily shed its heat, and so it resists fragmenting into small pieces. Instead, a pristine cloud can stay whole and hot and collapse as a single enormous mass. This is the very condition a black hole star requires, a huge cloud that does not break apart into ordinary stars but falls together into one monstrous object with a black hole at its heart. The chemical poverty of the early universe was not a limitation. It was the enabling condition. The first generation of stars born from this pristine gas were themselves strange and are thought to have been giants, far more massive than typical stars today, precisely because pristine gas resists fragmenting and tends to form larger objects. Astronomers call these first stars Population 3, and they have never been directly observed, only inferred, brilliant short-lived monsters that lit the first light and died in tremendous explosions, beginning the long work of seeding the universe with heavy elements. The black hole star belongs to this same lost era of cosmic firsts, the time of pristine gas and giant objects, before the chemistry of the universe grew rich and the rules of star formation settled into the gentler patterns we see today. This is also why black hole stars are confined to the deep past. As generations of stars lived and died, they enriched the gas with heavy elements, and once the gas was polluted, it cooled efficiently and fragmented readily, and the conditions for forming a black hole star vanished. These objects were a feature of the universe's chemical infancy, possible only while the gas was still clean. We will never find one nearby, in our own time, because our gas has been dirtied by 13 billion years of stellar death. The black hole star is a creature of a vanished world, and we can see it only by looking far enough back in time to reach the era when that world still existed. No one expects the chemical poverty of the early universe to be the very thing that made its strangest objects possible, but that is the deep logic of it. No one predicts that pristine gas, lacking everything that makes up the Earth and our bodies, would be exactly the gas that could fall together into a star with a black hole heart. And absolutely no one anticipates how thoroughly the rules of the cosmos have changed across its lifetime, how objects that were natural at the dawn became impossible later, leaving black hole stars stranded forever in the deep past, visible only as red light from a world that no longer exists. Walk with me through the question that follows. How do you make a heavy seed? How do you make a black hole of 100,000 suns directly in the early universe, without waiting for it to grow? And here, decades ago, theorists proposed a strange and elegant answer, an answer that brings us at last to the third door. They proposed that in the very early universe, before the heavy elements existed, a truly enormous cloud of pristine gas could collapse all at once, not fragmenting into many small stars the way gas clouds do today, but falling together into a single, monstrous object. And at the heart of that object, they argued, a black hole could form directly, while the vast envelope of gas around it survived. The black hole and its glowing shroud together would make a single structure, enormous, luminous, and utterly unlike any star that exists today. They called it a quasi-star, or more vividly, a black hole star. The idea of a black hole star did not appear out of nowhere when the red dots needed explaining. It is an old idea, sketched by theorists long before there was any evidence for it, and the history is worth knowing, because it shows how an idea can wait, patiently, in the margins of physics for decades until the universe finally produces the thing it described. The concept goes back, in its modern form, to theoretical work in the 2000s, when researchers including Mitchell Begelman and his colleagues were wrestling with exactly the seed problem we have discussed, the question of how the early universe could have built its supermassive black holes so quickly. They were looking for a way to make a heavy black hole seed directly, and they worked out the physics of what would happen if a truly enormous cloud of primordial gas, hundreds of thousands of times the mass of the Sun, collapsed without fragmenting into ordinary stars. What they found was that such a collapse could produce a peculiar, transient object, a vast bloated envelope of gas with a small black hole growing at its centre, the black hole feeding on the envelope and the energy of that feeding holding the whole structure up. They gave it the name quasi-star, a thing that is almost a star but not quite, and the name black hole star captures the same idea in plainer words. The theorists worked out, on paper, how such an object would behave. It would be enormous, far larger than any ordinary star, and relatively cool on its glowing surface despite the ferocious engine at its core, because the vast envelope would spread the heat over an enormous area. It would be short-lived by cosmic standards, lasting perhaps a few million years before the black hole consumed too much of the envelope and the structure came apart. And when it ended, it would leave behind a black hole far heavier than any ordinary stellar remnant, a ready-made heavy seed. Every piece of this was deduced from physics, decades before anyone could point a telescope at one. It was a prediction waiting for a confirmation that might never come. For a long time, that is exactly where it stayed, an elegant idea with no evidence. The kind of thing that appears in review papers about black hole seeds with the careful word hypothetical attached. Many beautiful ideas in physics live and die there, never confirmed, never refuted, simply unobservable. The black hole star might have remained one of them. What changed everything was Webb and the little red dots, and the slow realization that the strange properties of these objects matched almost eerily the decades-old predictions for what a black hole star should look like. The margin note was about to become a headline. No one expects an idea sketched on theoretical grounds in the 2000s to sit untouched for the better part of 20 years and then suddenly match a population of objects nobody knew existed when the idea was born. No one predicts that the universe would, decades later, hand us exactly the strange hybrid the theorists had described. And absolutely no one anticipates how often this happens in physics, how an idea can wait in the dark for a generation, patient and unproven, until the right instrument finally turns the right way and finds it waiting there, just as it was described. This is the third door, and let us walk all the way through it slowly, because it is the heart of tonight's story. A black hole star is, on the outside, something that looks star-like, a vast, glowing, bloated envelope of gas, thousands of times wider than the sun, shining with tremendous luminosity. But it is not powered the way a star is powered. An ordinary star shines by nuclear fusion in its core, hydrogen fusing into helium, the energy pushing outward against gravity. A black hole star has no fusing core. At its centre, where a normal star would have its nuclear furnace, there is instead a black hole. And the black hole is feeding, pulling in the surrounding gas of the envelope and the energy released by that feeding. The heat of matter falling toward the black hole is what holds the whole bloated structure up and makes it shine. It is a star powered not by fusion but by accretion, a star with a black hole for a heart, eating it slowly from the inside, while the envelope glows on around the wound. Tonight, we're going to do something different for a few minutes, and simply imagine standing near one of these objects, because we have described the black hole star in the language of physics and spectra, and it deserves, at least once, to be pictured as a place, a thing you could in principle behold. Picture yourself drifting in the young universe, a billion years or so after the Big Bang, in front of a black hole star. The first thing you would notice is the sheer size of it. This is not a point of light like an ordinary star seen from far away. It is a vast, glowing sphere, thousands of times wider than our sun, so large that it would fill your entire view, a wall of deep red and orange light curving away in every direction, more like a glowing sky than a star. Its surface, despite the monstrous engine at its core, would be relatively cool by stellar standards, glowing in those deep reds and dull oranges rather than the fierce white of our sun, because all the heat of the central black hole is spread across such an immense surface that the outside never reaches white heat. It would look, from outside, almost gentle, a great soft bloated lantern of crimson light hanging in the dark. But the gentleness would be an illusion, a mask over the violence within. Far below that calm red surface, down through thousands of times the depth of an ordinary star, at the very centre there would be the black hole, small and absolute, feeding. Gas would be spiralling inward through the vast envelope, heating as it fell, blazing as it approached the central darkness, the energy of that infall pouring back outward to hold the whole enormous structure up. The serenity of the red surface would be the surface of a thing being devoured from within, the calm exterior of an object whose heart is an abyss steadily eating everything around it. You would be looking at the largest, strangest furnace in the universe, disguised as a quiet red glow, and it would not last. If you could somehow watch it across the few million years of its life, sped up, you would see the great red sphere slowly change as the black hole at its heart grew and consumed more and more of the envelope. Eventually the balance would tip, the structure would begin to come apart, the great red lantern guttering and dispersing, the glowing gas blowing away into the surrounding space. And when the last of the envelope cleared, the disguise would fall away entirely, and what remained would be the black hole itself, naked now, vastly heavier than it began, a dark seed left, sitting in the early universe where a glowing red star had been, ready to begin its long career at the centre of a forming galaxy. There is something genuinely strange and beautiful in holding that image, the great soft red sphere with the abyss at its heart, and knowing that it is not fantasy, that the universe really made these things by the thousands, and that their light, the deep crimson glow of their enormous calm surfaces, is exactly the little red dots that Webb has been finding. When you look at one of those faint red specks in a Webb image, you're looking at that vast glowing lantern, shrunk by 13 billion light-years of distance to a single point, its calm red surface and its devouring heart folded together into a smudge you could cover with a fingertip. The dot is the lantern. The lantern is real. And somewhere inside it then, the dark was quietly feeding. No one expects the largest furnace in the universe to look, from outside, like a soft and gentle red glow. But that is the disguise of a black hole star. No one predicts that the calm, crimson surface of such an object hides an abyss steadily eating it from within. And absolutely no one anticipates how much feeling there is in the picture. Once you let yourself hold it, a great soft lantern of red light, beautiful and doomed, with a shadow at its heart, glowing out across 13 billion years toward the telescope that would finally see it. No one expects a star and a black hole to coexist in the same object, the one wrapped around the other, the dark centre feeding on the bright shell. No one predicts that the solution to the early universe's biggest black holes would be an object that is half star and half abyss. And absolutely no one anticipates how perfectly such an object, if it were real, would explain the little red dots, because a black hole star would look exactly like what Webb had been seeing, neither a pure galaxy of stars nor a naked quasar, but a feeding black hole wrapped in a thick, glowing, reddening envelope of gas. The third door, the one no one had been able to confirm, fit the evidence better than either of the other two. All that was missing was proof. Proof is hard to come by when your target is a tiny red speck 13 billion light-years away. The little red dots are so faint and so distant that, for most of them, all astronomers could collect was a smudge of light, enough to know the object was there, not enough to read its secrets. To truly test the black hole star idea, astronomers needed a spectrum, the light of a single red dot spread out into all its individual colours, fine enough to read the fingerprints of the gas and the black hole within, and gathering a spectrum that detailed from an object that faint would normally take an impossible amount of telescope time. So astronomers used a trick, one of the most beautiful in all of observational astronomy. They let the universe build them a bigger telescope. Between us and the deep cosmos lie great clusters of galaxies, and a cluster of galaxies contains so much mass that its gravity bends the space around it and bends the path of any light passing through. A cluster, in other words, acts as a lens, a vast natural magnifying glass, gathering and focusing the light of whatever sits behind it. Astronomers call this gravitational lensing, and it lets us see objects far fainter and farther than any telescope could reach on its own. Point Webb at the right cluster, and a faint red dot hiding behind it can be magnified, brightened, its light amplified by the gravity of 1 trillion suns. Tonight, we're going to spend a few minutes on the trick that made this discovery possible, gravitational lensing, because it is one of the most beautiful tools in all of astronomy, and without it the spectrum of glimpse, Nvias 775 could never have been gathered. The idea comes straight from Einstein. Mass bends space, and light travelling through bent space follows a curved path. So when light from a distant object passes near a great concentration of mass, a galaxy cluster say, its path is bent, focused, the way a glass lens bends light. A galaxy cluster, holding the mass of 1,000 trillion suns, is a tremendously powerful lens. Light from a distant object behind it gets gathered and magnified, brightened, sometimes split into multiple images, sometimes stretched into long, glowing arcs. The cluster becomes a natural telescope, free, enormous, built by gravity, sitting in space waiting for us to use it. For faint distant objects, this is transformative. A little red dot 13 billion light-years away is, on its own, almost too faint to study in detail. But place a galaxy cluster between us and that red dot, lined up just right, and the cluster's gravity can magnify the dot's light by a large factor, gathering far more of its photons into our telescope than would otherwise arrive. In the case of Glimpse S17S75, behind the cluster Abell S1063, the magnification meant that 30 hours of Webb's time delivered roughly what 80 hours would have without the lens. The cluster did the extra 50 hours of work for free, simply by being massive and being in the way. This matters enormously, because telescope time is the scarcest resource in astronomy. Webb is the most sought-after instrument in the history of the science, and every hour is fought over by researchers around the world. To gather a spectrum detailed enough to read 40 separate lines from a single faint red dot would, without lensing, require an amount of telescope time so vast it might never be granted. Gravitational lensing makes the impossible merely difficult. It lets us reach objects that would otherwise lie forever beyond our grasp, by borrowing the gravity of the great clusters that happen to sit in the right place. There is something quietly wonderful in the fact that to see one of the universe's strangest small objects, we had to use one of its largest structures as a magnifying glass. The cluster and the red dot have nothing to do with each other. The cluster is merely in the foreground, billions of light-years closer, an accident of alignment. But its gravity, reaching across space, gathered up the ancient light of the red dot behind it and delivered that light to us, amplified 80 hours worth in 30, just enough to read the secret it carried. The universe, in effect, helped to study itself. No one expects to need a whole cluster of galaxies just to read the light of a single distant speck, but that is the scale the early universe demands of us. No one predicts that the gravity of a foreground giant would be the thing that finally cracked the case of the little red dots, lending us the reach our telescopes lack. And absolutely no one anticipates how often the deepest discoveries depend on these lucky alignments. A great mass in the foreground, a faint riddle behind it, and the patient light of the early universe bent gently into focus by the curve of space itself. That is exactly what was done. Behind a galaxy cluster called Abell S1063, there sat a little red dot, and the cluster's gravity magnified it enormously. Webb devoted 30 hours to staring at it, and the lensing made those 30 hours count like roughly 80. The natural magnifying glass of the cluster stretching the telescope's reach far beyond its normal limit. The object has a catalogue name, Glimpse 1cent/75, and we see it as it was about 1.5 billion years after the Big Bang. And out of those long magnified hours came the prize, the most detailed spectrum of a little red dot ever captured, a record of its light containing more than 40 separate spectral lines, more than had ever been read from one of these objects before. Tonight, we're going to understand how astronomers can possibly know what a distant object is made of and what is happening inside it from nothing but its light. The answer is spectroscopy, and it is, quietly, one of the most powerful ideas in all of science. When you spread light out into its component colours, the way a prism turns sunlight into a rainbow, you get a spectrum. And a spectrum is not smooth. It is crossed by sharp lines, bright lines where certain colours are unexpectedly strong, and dark lines where certain colours are missing. These lines are fingerprints. Each chemical element, when it is hot or when it absorbs light, emits or swallows very specific colours, a pattern as unique as a barcode. Hydrogen has its pattern, helium has another, iron has a dense and complicated one. So by reading the lines in an object's spectrum, astronomers can tell what it is made of, how hot it is, how fast it is moving, how dense its gas is, and much more, all from light that left the object billions of years ago. The whole chemistry and physics of a distant thing is written in the fine structure of its light, if you can only collect enough of it to read. This is why the spectrum of Glimpse 1cent/75 mattered so much, and why it took 80 hours of effective telescope time to gather. A faint smudge tells you almost nothing, but a detailed spectrum with 40 separate lines resolved tells you nearly everything. And when astronomers read those lines, the story they told was specific and strange. There were dense thickets of iron lines, what astronomers vividly call an iron forest, and such forests form only in thick, relatively cool, dense gas pressed close around a powerful light source. There were lines from helium being excited by fierce radiation. And there was that telling feature, the Balmer break, a particular step in the brightness of the light across a certain boundary of colour. The Balmer break is the detail worth dwelling on, because it is the kind of clue that turns a hunch into a case. In an ordinary galaxy, a Balmer break is produced by stars, specifically by the combined light of a galaxy's stellar population, and finding one is normally taken as a sign that you are looking at starlight. For a while, the Balmer breaks seen in some red dots were used to argue that they must be galaxies full of stars after all. But the detailed spectrum suggested something different. The break in Glimpse 1cent/75 and objects like it appears to be produced not by stars but by the dense gas itself, the thick envelope absorbing and reshaping the black hole's light in a way that mimics the stellar feature. The very clue that seemed to point towards stars turned out on closer reading to point toward a black hole wrapped in dense gas. The fingerprint had been misread, and the finer spectrum corrected it. That is the power and the subtlety of spectroscopy. The same feature can mean two different things depending on what produces it, and only a detailed enough spectrum can tell them apart. The 40 lines of Glimpse 1cent/75 were detailed enough. Read together, the iron forest, the excited helium, the gas-made Balmer break, the signature of a rapidly feeding black hole buried in a cocoon, they pointed past both of the old doors and through the third to the black hole star. The object had been telling us what it was all along, in the fine print of its light. We simply needed to gather enough of that light to read the fine print clearly. No one expects the entire nature of an object 13 billion light-years away to be legible in the fine structure of its light, but it is, if you can collect enough of it. No one predicts that a single feature, the Balmer break, could be read first as a sign of stars, and then, more carefully, as a sign of dense gas around a black hole, flipping the conclusion entirely, and absolutely no one anticipates how much certainty can be wrung from so faint a source, how 40 lines of crimson light, gathered over 80 hours of borrowed gravity, can crack a 3-year mystery and point to the strangest object in the early universe. Now let's begin reading what that spectrum said, because this is the moment the case cracked open. When astronomers spread the light of Glimpse 1775 into its colours and studied the lines, they did not see the signature of a galaxy quietly full of stars. They saw the signature of a rapidly feeding black hole, but a feeding black hole wrapped in something, buried inside a dense, thick cocoon of gas. The gas was absorbing the fierce light from the black hole and reprocessing it, reshaping it, before it escaped. And the specific fingerprints in that reprocessed light matched, with remarkable precision, what the decades-old black hole star models had predicted. The spectrum looked, in key ways, more like the outer layers of a bloated cool star than like a naked quasar, even though the energy underneath was unmistakably a black hole. The light was star-like on the surface and black hole-driven at the core, exactly the hybrid the third door demanded. There were specific, telling details. The spectrum showed dense forests of iron lines, the marks of thick, relatively cool gas pressed close around the light source. It showed the fingerprints of helium being lit by radiation. It showed a particular feature, a kind of step in the light called a Balmer break, that in an ordinary galaxy is made by stars, but here appeared to be made by the dense gas itself rather than by starlight, which is exactly what a black hole star wrapped in a thick envelope should produce. Feature after feature pointed the same way. Not a galaxy of stars, not a bare quasar, a black hole, feeding, swaddled in a vast dense shell of gas that reprocessed its light into the deep red glow we see. A black hole star. Pattern interrupt. Sit with the weight of this for a moment, because it is the turn the whole night has been building toward. For 3 years the little red dots had refused every explanation, caught between 2 doors, fitting neither, and here, in a single object, magnified by the gravity of an entire galaxy cluster, stared at for the equivalent of 80 hours, the third door finally swung open, and behind it was exactly the strange hybrid the theorists had sketched decades before and almost no one had expected to see. Expectation. The red dots would turn out to be a more ordinary thing, a known category we had simply mismeasured. Reality. They appear to be black hole stars, objects so strange they had lived only in theory, stars with feeding black holes for hearts, scattered by the thousands across the cosmic dawn. No one expects a decades-old theoretical curiosity to walk out of the margins and into the data fully formed, but that is what the spectrum of Glimpse 1775 seems to show. No one predicts that the answer to 1,000 impossible objects would be a single magnified speck, read line by line out of 80 hours of borrowed gravity. And absolutely no one anticipates how much else falls into place, how many other mysteries quietly resolve, the moment you accept that the little red dots are stars with black holes hidden inside them. Glimpse 1775 was the clearest case, the most detailed spectrum, the strongest single clue. But it did not arrive in isolation, and it is worth knowing that the evidence for black holes inside the red dots had been quietly accumulating from several directions before this one object brought it all into focus. Over the past couple of years, as astronomers gathered spectra of more and more red dots, a pattern had been emerging. Many of them showed signs of fast-moving gas, the kind of broad spectral features that indicate gas whirling at high speed, which is one of the classic signatures of a black hole's gravity at work, pulling nearby gas into rapid motion. These broad features were hard to explain with stars alone and pointed again and again toward a feeding black hole hidden somewhere in each object. Individually, each was suggestive rather than conclusive. Together they built a growing case that whatever the red dots were, black holes were central to them. There were specific landmark objects along the way. Astronomers studied particular red dots in detail, and gave their investigations names, and in several of them they found the same troubling, exciting combination, the signature of a black hole, but wrapped in something, muffled, reddened, lacking the full violent brilliance of an ordinary quasar. One closely studied object showed a Balmer break that, on careful analysis, appeared to come from dense gas around a black hole rather than from stars, an early hint of exactly the conclusion the glimpse 1.775 spectrum would later sharpen. Another showed a black hole that seemed to dominate its tiny host entirely. Piece by piece, object by object, the picture of a black hole shrouded in dense gas kept reappearing, the same strange profile emerging from different red dots studied by different teams. This is how scientific confidence is actually built, and it is worth understanding, because it is less dramatic and more trustworthy than the way discoveries are often told. It is rarely a single observation that settles a question. It is the slow convergence of many independent clues, each one imperfect, each one arguable on its own, all pointing the same way until the weight of them becomes hard to deny. The broad gas motions in many red dots, the muffled black hole signatures, the inverted galaxies like Abell 2744 QS01, the gas-made Balmer breaks, and finally the richly detailed spectrum of glimpse 1.775. All of these are separate threads, and they are braiding together into a single strong rope. No one thread holds the full weight. The rope does. That convergence is what makes the black hole star the leading explanation now, rather than just one idea among many. It is not resting on a single measurement that might turn out to be a fluke. It is resting on a growing body of evidence from many objects and many teams, all of it pointing toward black holes shrouded in dense gas at the cosmic dawn. The glimpse 1775 spectrum was the clearest single view, but it confirmed and sharpened a picture that had been forming for a while. That is exactly the kind of evidence that tends to survive, because it does not depend on any one observation being perfect. No one expects scientific certainty to be built quietly, thread by thread, rather than in a single dramatic stroke, but that is almost always how it happens. No one predicts that the case for black hole stars would be assembled from a dozen partial clues across years of work, each one too weak alone, all of them strong together. And absolutely no one anticipates how much sturdier a conclusion becomes when it rests not on one brilliant measurement, but on the patient convergence of many, all the separate riddles of the red dots braiding slowly into a single answer. Tonight, we're going to spend some time on what falls into place, because this is where the black hole star idea stops being a curiosity and starts being a key that opens several locked doors at once. Begin with the problem we started from, the universe-breaking galaxies. Remember that the first door, the idea that the red dots are galaxies made of stars, demanded an impossible number of suns assembled impossibly fast, and that this was the thing generating headlines about web-breaking cosmology. If the red dots are black hole stars, that crisis simply dissolves. The red light is not the combined glow of hundreds of billions of stars after all. It is the glow of gas around a feeding black hole. You do not need an impossible mountain of stars to explain the brightness, because most of the light was never coming from stars. The objects that seemed to break the model were never made of what we thought. The model bends back into shape. The universe did not assemble impossible galaxies at the cosmic dawn. It made black hole stars, and we misread their light. Now take the older, deeper problem, the seed problem, the question of how the early supermassive black holes got so big so fast. The black hole star is, in a sense, the perfect incubator, and this is the most beautiful part of the whole picture. Inside a black hole star, the central black hole sits buried in a vast dense envelope of gas, and it feeds on that envelope continuously, steadily, for as long as the envelope lasts. Crucially, the thick envelope shields the black hole from its own violence. Normally, a feeding black hole shines so fiercely that its own radiation blows away the very gas it is trying to eat, choking off its growth, putting a speed limit on how fast it can grow. But inside a black hole star, the dense envelope absorbs and contains that radiation, holding the food in place, letting the black hole eat far faster and far longer than a naked black hole ever could. The black hole star is a feeding machine, a cocoon built to grow a black hole at maximum speed. By the end of tonight, you're going to see how neatly this closes the circle. A black hole star starts with a heavy seed, formed when a huge pristine cloud collapses directly. The black hole at its heart then feeds, sheltered and rapid inside the envelope, growing quickly toward intermediate size, and when the envelope is finally exhausted, consumed or blown away, what is left behind is a black hole far heavier than any ordinary stellar seed, sitting in the early universe with a tremendous head start, ready to grow on into one of the supermassive giants we see anchoring galaxies today. The black hole star is the missing middle, the bridge between the pristine gas of the cosmic dawn and the monsters that now sit at the centres of galaxies. The red dots are not just a curiosity, they may be the very nurseries where the universe's giant black holes were born. By the end of tonight, you are going to understand the thread that runs forward in time from these ancient red dots to the universe we actually live in, because if the black hole star idea is right, then these objects are not just a curiosity of the distant past. They are our own beginning, the ancestors of the giants that shape every galaxy today, including ours. Consider where the supermassive black holes ended up. In the modern universe, virtually every large galaxy has one at its centre. Our own Milky Way harbours a black hole of about 4 million solar masses at its heart, the one we call Sagittarius A star, the one whose silhouette was photographed by the Event Horizon Telescope. The galaxy M87 holds a far larger one, 6.5 billion solar masses, the first black hole ever directly imaged, that famous orange ring. These giants are everywhere, one to a galaxy, sitting quietly at the centres of the great star systems, their gravity helping to anchor and shape the galaxies around them. They're a standard feature of the cosmos, as ordinary as galaxies themselves. And here is the question the black hole star may answer. Where did all of these giants come from? How does every large galaxy come to have one? And how did they get their start? If black hole stars were common at the cosmic dawn, as the thousands of red dots suggest, then they may be the origin of the whole population. Each black hole star manufactured a heavy seed, a black hole of tens or hundreds of thousands of solar masses, and handed it off to grow within a forming galaxy. Over the following billions of years, those seeds fed and merged and grew into the supermassive giants we see today. The red dots in this picture are the seed factories of the universe, the place where nearly every central black hole, including the one at the heart of our own galaxy, may have gotten its start. Think about what that means for Sagittarius A star, the black hole at the centre of the Milky Way. If this picture is right, then more than 13 billion years ago, it may have begun as a black hole star, a glowing red object with a feeding shadow inside it, one of the thousands scattered across the cosmic dawn. It shed its envelope, emerged as a heavy seed, and over the long ages grew and settled into the quiet giant that now anchors the galaxy you live in. The dark heart of our own Milky Way may have a youth, a glowing red infancy at the dawn of time, and the little red dots Webb is finding may be, in a real sense, snapshots of what our own galaxy's central black hole once was. Pattern interrupt. There is a deep continuity in this, a thread that runs unbroken from the cosmic dawn to the night sky over your home. The same kind of object that glows as a little red dot 13 billion light-years away may have become, after eons of growth, the silent giant at the centre of our galaxy, around which the sun and the earth and you yourself slowly turn. The red dots are not a separate alien chapter of cosmic history. They are the first page of our own, the beginning of the story that leads to the black hole at the heart of the Milky Way, and to the night you are resting under right now. No one expects the strange red specks of the cosmic dawn to be the ancestors of the familiar giant at the centre of our own galaxy. But that may be exactly the relationship. No one predicts that Sagittarius A star, the black hole the Milky Way turns around, might once have been a glowing red object like the ones Webb is finding. And absolutely no one anticipates how unbroken the thread turns out to be, how the first hearts of darkness at the dawn of time lead, across 13 billion years, straight to the quiet centre of the galaxy you call home. Glimpse. 1605 was not the first red dot to point toward a black hole. There was an earlier object that gave the whole field one of its loudest shocks, and it is worth meeting, because it shows how strange these things are even before you reach the black hole star idea. Behind another galaxy cluster, the famous Pandora cluster, also known by its catalogue name Abell 2744, sits a little red dot that astronomers labelled Abell 2744 QS01. It was first picked out in 2023, again with the help of gravitational lensing, the great cluster magnifying the faint object behind it. And when astronomers measured it, they found something that broke their intuition. The object contained a black hole of roughly 50 million times the mass of the Sun, existing only about 700 million years after the Big Bang. That alone is remarkable. But the truly shocking part was the comparison between the black hole and the tiny galaxy around it. In the universe, we know there is a tight relationship between a galaxy and the black hole at its centre. The black hole is always a small fraction of the galaxy, typically about 0.1% of the mass of all the galaxy's stars. Big galaxy, proportionally big black hole. Small galaxy, small black hole. This relationship is so reliable that astronomers treat it as a bedrock fact, evidence that galaxies and their black holes grow up together in step over cosmic time. But Abell 2744 QS01 shattered that proportion. Its black hole was not 0.1% of the surrounding stars. By some measures it was comparable to, or even heavier than, all the stars in its tiny host combined. The black hole did not sit politely at the centre of its galaxy. The black hole nearly was the galaxy. The proportion was not bent, it was inverted. Now, let's begin with a deeper reason the inverted galaxies like Abell 2744 QS01 are so startling, and it is worth understanding because it concerns one of the most surprising relationships in all of astronomy, a connection between two things that seem like they should have nothing to do with each other. The black hole at the centre of a galaxy is, in physical terms, tiny compared to the galaxy around it. A supermassive black hole might be a few million times the mass of the Sun, while the galaxy holding it contains hundreds of billions of stars. The black hole's gravitational reach extends only over a minuscule region at the very centre, vanishingly small compared to the vast bulk of the galaxy spreading out for tens of thousands of light years around it. By all rights, the black hole and the outer galaxy should be almost completely independent. The tiny central object and the enormous structure around it, each going about its business with no knowledge of the other. The black hole should be like a single grain of sand at the centre of a city, far too small to matter to the city as a whole, and yet they are linked, tightly, mysteriously. Astronomers discovered, studying galaxy after galaxy, that the mass of the central black hole is closely tied to the properties of the whole surrounding galaxy, in particular to how fast the galaxy's stars move. The bigger the black hole, the faster the stars throughout the galaxy swarm in a tight and predictable proportion. This relationship is called the M-sigma relation, and it is one of the most studied and most puzzling facts in galaxy science, because it should not exist. How does a tiny central black hole come to be so precisely matched to the motion of stars spread across the entire galaxy? Stars so far away that the black hole's gravity barely touches them? Something must coordinate them, some process that ties the growth of the little black hole to the growth of the whole galaxy. The leading explanation is a kind of feedback, a self-regulating loop. As the black hole feeds and grows, it pours out tremendous energy, and that energy pushes back on the surrounding gas, heating it and driving it away, which limits both how much more the black hole can eat and how many more stars the galaxy can form. The black hole, in effect, regulates its own galaxy, and the galaxy regulates the black hole, the two growing together in a balanced dance, each one's growth tied to the others through the gas they share. Over billions of years, this co-regulation produces the tight M-sigma relation, the black hole and the galaxy ending up precisely matched because they grew up together, each shaping the other. It is a partnership written across cosmic time. Now you can see why the inverted early objects are such a shock. Abell 2744, QS01, with its black hole as massive as or heavier than all the stars around it, completely violates the M-sigma relation. The partnership has not been established yet. The black hole is enormous, and the galaxy is tiny. The proportion wildly out of balance, as though the black hole arrived first and the galaxy had not yet caught up. And this fits the black hole star picture perfectly. If black holes form first, directly, as heavy seeds inside black hole stars, then in the earliest times they would naturally be overmassive, far too big for their barely formed galaxies, and the famous M-sigma balance would only be established later, as the galaxies grew up around the black holes that were already there. The tight relationship we see today would be the end state of a long process that began with the black holes far ahead, the galaxies catching up over billions of years. No one expects a tiny central black hole to be precisely matched to an entire galaxy it can barely touch. But the M-sigma relation says it is, one of the deep puzzles of the field. No one predicts that the early universe would show us that relationship before it formed, the black holes overmassive and the galaxies not yet caught up. And absolutely no one anticipates how the black hole star resolves even this, explaining not just the red dots and the seeds and the giants, but the very origin of the strange lifelong partnership between a galaxy and the shadow at its heart. And there was a second strange detail, a chemical one. If the little galaxy around the black hole had formed in the ordinary way, building up stars over time, those stars would have lived and died and enriched the surrounding gas with heavy elements, oxygen, carbon, iron, the ash of stellar death. But the gas around Abell 2744 QS01 was found to be remarkably pristine, strikingly poor in heavy elements, as though very little ordinary star formation had happened there at all. The black hole was enormous, and the galaxy around it was not only tiny but chemically untouched, as if the black hole had arrived first, before the stars had a chance to build a proper galaxy and seed it with their ashes. You can see how naturally this points toward everything we have discussed tonight. An overmassive black hole, far too big for its tiny pristine host, sitting at the cosmic dawn, is exactly what you would expect if the black hole formed first, directly from a heavy seed, and the little galaxy was only beginning to gather around it. Abell 2744 QS01 was, in a sense, an early warning, a single red dot that already whispered the answer before Glimpse Wasenten Centers and Seven Fumbas have spelled it out. The black holes came first, the galaxies came second. The proportion we trust in the modern universe simply had not been established yet, because at the cosmic dawn, the dark hearts arrived before the light could build around them. No one expects to find a black hole that outweighs its own galaxy, but Abell 2744 QS01 is very close to exactly that, the proportion turned upside down. No one predicts that the gas around such a monster would be pristine, almost untouched by stellar death, as though the stars had barely begun. And absolutely no one anticipates how clearly this single object foreshadowed the larger answer. A black hole first and a galaxy after, the dark centre predating the starlight, the seed arriving before the soil. There is something almost poetic in the order of it, and it is worth pausing on. We have always told the story of the cosmos as light first, then darkness, stars igniting to push back the black, galaxies forming, and only later the black holes growing fat at their centres. The black hole star suggests a stranger order. In these objects, the darkness is at the centre from the very start, the black hole already present, already feeding, and the light is the shell around it, the glowing envelope that the darkness consumes. The shadow does not come after the light here. The shadow is the heart, and the light is wrapped around it, and the light is slowly being eaten. The early universe in this picture was full of these hearts of darkness clothed in red fire, thousands of them, scattered across the first billion years, each one quietly growing a monster inside itself. By the end of tonight, you're going to understand one quality of the black hole star worth dwelling on before we close, because it makes these objects even rarer and more precious than they first appear, and it is the matter of time. A black hole star is fleeting. By the standards of the cosmos, it barely exists at all. The whole glowing phase from the formation of the object to the dispersal of its envelope lasts perhaps a few million years. A few million years sounds like a long time, and by human measure it is unimaginably long. But against the age of the universe, nearly 14 billion years, a few million years is the merest flicker, less than 1,000th of cosmic history, the blink of an eye in the life of everything. The black hole star ignites, glows its deep red glow, feeds its central darkness, and is gone, all within a span that the universe would scarcely notice. This means that when we catch a little red dot in a web image, we're catching something in a very brief moment of its existence, a moment that, for that particular object, ended billions of years ago. Each red dot is an object that glowed for an instant of cosmic time and then transformed, shedding its envelope, leaving behind a naked black hole that would go on to a long, dark, quiet career while the red glow that betrayed its birth faded forever. We are not seeing these objects as they persisted. We are seeing them in the single brief chapter when they were visible at all, frozen in the light that happened to be leaving them during their short, bright phase. And yet, despite how fleeting each one is, Webb finds them in their thousands. That tells us something striking. If objects that each last only a few million years are nonetheless common in our images of the early universe, then there must have been an enormous number of them overall, far more than we directly see, because at any given moment we can only catch the small fraction that happened to be in their brief glowing phase right then. It is like glimpsing a field at night and seeing a few hundred fireflies lit at once, and realizing that the field must hold many thousands, because each one glows only for an instant and most are dark at any given moment. The thousands of red dots we see imply a vast hidden population of black hole stars across the cosmic dawn, most of them caught in our images only because we are looking at an enormous stretch of early cosmic time all at once. There is a poignancy in the brevity, and it is the note I want to carry toward the close. Each of these objects was a brief, brilliant event, a few million years of red light in the dark, and then a long silence. They were the universe's fireflies, lighting up for an instant at the dawn of time, manufacturing the seeds of the giants and then going dark. Almost all of them finished glowing billions of years before the Earth formed, and the light from the few we can see has been travelling toward us across all that time, carrying the memory of a brief glow that ended before our world began, arriving at last as a scatter of faint red dots in the eye of a telescope built by creatures who came long, long after the fireflies went out. No one expects the objects that built the universe's giant black holes to have been so fleeting, glowing for only a flicker of cosmic time before vanishing, but that is the nature of a black hole star. No one predicts that finding thousands of such brief objects would imply a vast hidden multitude, most of them dark at any given moment, like fireflies in a night field. And absolutely no one anticipates how moving their brevity becomes. These brief red fireflies of the cosmic dawn, each one glowing for an instant, seeding a monster and going dark, their last light only now arriving across 13 billion years to tell us they were ever there at all. Tonight we're going to follow the life of a single black hole star from beginning to end, because tracing its whole arc, birth to death, makes the strange object feel real in a way that no static description can. It begins in the dark, a few 100 million years after the Big Bang, with a cloud. Not an ordinary cloud, but an enormous one, hundreds of thousands of times the mass of the Sun, made of nearly pristine gas, hydrogen and helium, almost untouched by the heavy elements that ordinary stars would later spread through the cosmos. In most circumstances, such a cloud would fragment, breaking into many pieces, each piece collapsing into its own star, the way star clusters form. But under the right conditions, perhaps bathed in radiation that prevents it from cooling and fragmenting, the cloud does something else. It stays whole, and it falls together, all of it, into a single collapsing mass. At the centre of that collapse, gravity wins so completely that a black hole forms directly, while the vast outer envelope of gas, too far out to fall in immediately, remains swirling, glowing, held up. Now the black hole star is born, and it enters its brief, brilliant life. The central black hole feeds on the inner envelope, and the energy of that feeding pours outward, heating the enormous shell of gas, holding it up against its own gravity, making it shine. From the outside, it is a colossal glowing object, far larger than any ordinary star, perhaps thousands of times the width of the sun, its surface relatively cool and deep red despite the furnace at its core, because that core's heat is spread across such an immense surface. It is luminous beyond ordinary stars, and it is red, and it is compact compared to a galaxy, exactly the profile of a little red dot. For a few million years, this strange equilibrium holds, the black hole feeding, the envelope glowing, the whole structure shining across the young universe. But it cannot last, and here is the melancholy of it. The black hole is eating the very envelope that sustains the structure. As it feeds, it grows, and the envelope shrinks, and the balance slowly tips. Eventually the black hole has consumed or driven away too much of the gas that held the whole thing together, and the structure comes apart. The glowing envelope disperses, blown off or swallowed, and the disguise falls away. What is left, at the end, is the black hole itself, now grown far heavier than any ordinary stellar remnant, a naked seed of perhaps tens or hundreds of thousands of solar masses, sitting in the early universe, stripped of its shell, ready for the next phase of its life, the long, slow growth into a supermassive giant. So the black hole star is a chrysalis, in a sense. It is the temporary form, the cocoon stage, in which a heavy black hole seed is manufactured and grown in shelter before it emerges, naked and massive, to begin its real career at the centre of a forming galaxy. The red dots we see are these objects caught in their chrysalis phase, glowing, feeding, briefly visible, on their way to becoming the dark giants that will anchor galaxies for the rest of cosmic time. Every supermassive black hole in the modern universe, perhaps, passed through a stage like this, a few million years of glowing red in the cosmic dawn, before settling into the long, dark quiet at a galaxy's heart. No one expects a black hole to have a youth, a glowing larval stage, a chrysalis it grows in, and then sheds. But that is what the black hole star seems to be. No one predicts that the dark giants at the centres of galaxies, including our own, might each have begun as a brief red star with a feeding shadow inside it. And absolutely no one anticipates how tender the picture becomes when you trace the whole arc. A pristine cloud, a brief brilliant glowing life, and then the quiet emergence of the grown black hole, stepping out of its shared envelope into the long darkness of its adulthood. No one expects the order of creation to run darkness first and light around it, but that is what the black hole star implies. No one predicts that the thousands of little red dots would turn out to be the cradles of the supermassive black holes, the place the universe's giants were grown, and absolutely no one anticipates how much of cosmic history rearranges itself around this one strange object, how the universe-breaking galaxies and the impossible early giants and the puzzling red dots all turn out to be three faces of a single answer, a star with a black hole hidden inside it. We should be honest, before we close, that this is still new, and science is careful for good reason. The spectrum of glimpse, 1 10⁻⁵, is the strongest evidence yet But it is one object, and extraordinary claims earn their place only by surviving many more looks. There are astronomers who urge caution, who note that the red dots may not all be the same kind of thing, that some may still be dusty galaxies, that the black hole star interpretation, beautiful as it is, must be tested against many more spectra before it is settled. This is not the field declaring victory. It is the field finding its strongest clue yet and saying carefully, "This looks right, and now we must make sure." That patience is not a weakness in the story. It is the part that makes the eventual answer trustworthy. Let us pause in the middle of all this strangeness and let the scale of what we are seeing settle into something the body can hold, because the numbers are so large that they can stop meaning anything, and that is a loss worth resisting. When you look at a little red dot in a Webb image, you are looking at light that left its source more than 13 billion years ago. Hold that against the age of the Earth, which is 4.5 billion years. The light from these red dots began its journey toward us nearly 3 times longer ago than the Earth has even existed. When that light set out, there was no sun, no Earth, no solar system at all, only the young universe, less than 1 billion years past its own beginning. The light crossed the growing void for billions of years before the Earth formed beneath its path, and then for billions more while life arose and oceans filled and continents drifted, and it arrived, finally, in the mirror of a telescope built by creatures who evolved on a world that did not exist when the light began. The red dot you see is not a thing as it is. It is a message from a sender that ceased to exist in that form before the Earth was born. And consider what each dot actually is, in physical scale. A black hole star, if that is what these are, might be thousands of times the width of our Sun, an object so large that if you placed it where the Sun sits, it could swallow the orbits of the inner planets whole. Its central black hole alone might weigh tens or hundreds of thousands of times the mass of the Sun, and yet, across 13 billion light-years, all of that, the vast glowing envelope, the monstrous feeding shadow at its heart, the whole impossible structure, arrives as a single dim red speck, smaller in our images than almost anything else we study, a dot you could cover with the tip of a pin. The largest and strangest objects reduced by distance to the faintest of marks. There is a particular vertigo in this, and also a particular wonder. We are looking at the universe's infancy, at objects that were already ancient and already gone before our world began, and we are reading their inner workings, the chemistry of their gas, the nature of their hidden hearts, from a few dozen lines in a smear of crimson light. The gap between how little reaches us, a faint red dot, and how much we can know from it, the entire nature of a black hole star, is one of the quiet miracles of the science. Almost nothing arrives. From that, almost nothing, we reconstruct a world. Pattern interrupt. This is the thought I want to leave you holding, in the quiet. Every little red dot is a candle that was lit at the dawn of the universe, burned for a few million years, and went out billions of years before there was anyone to see it. The light kept travelling anyway, patient, unhurried, across an expanding cosmos for 13 billion years, carrying its small red message toward a telescope that would not be built until the very end of that journey. And we caught it. After everything, after all that time and all that distance, we were here, with the right cold mirror pointed the right way, to receive the last of that ancient light, and finally understand what it had been trying to tell us. The dot is small. What it carries is the dawn of everything. No one expects to hold the infancy of the universe in a speck of crimson light, but that is what a little red dot is. No one predicts that the faintest marks in our deepest images would carry the most complete stories, the entire life of a black hole star folded into a smear, and absolutely no one anticipates how moving it is, once you sit with it, that the universe kept these candles burning toward us across 13 billion years, and that we arrive just in time to read them. Before we begin, let us clear away a few misunderstandings about all of this, because the little red dots and black hole stars are exactly the kind of topic that grows tangled, and the truth is cleaner and more interesting than the tangles. The first misunderstanding is that a black hole star is just a black hole with some gas around it, which is true of almost every feeding black hole and would make the term meaningless. The distinction is real and specific. In an ordinary feeding black hole, the gas forms a flat, fast-spinning disk, and the system shows the violent signatures of that disk, fast motion, X-rays, the unmistakable look of a quasar. A black hole star is different. The black hole is buried in a vast, roughly spherical, dense envelope so thick that it traps and reprocesses the light, smothering the usual violent signatures and producing instead something that looks, on the surface, almost like a bloated, cool star. It is the thickness and shape of the envelope, and the way it disguises the black hole as something star-like, that makes a black hole star its own category, not just a black hole with a little gas nearby. The second misunderstanding is that this discovery means the little red dots are definitely, every one of them, black hole stars. That is more than the evidence supports, and the careful astronomers are the first to say so. The strong spectrum of GLIMPS 1 to 10 to 1075 is the best evidence yet that at least some red dots are black hole stars, and the interpretation fits the broader population strikingly well. But the red dots are a large and varied population, and it remains possible that some are dusty galaxies, some are more ordinary obscured quasars, and some are black hole stars. A mix rather than a single uniform answer. The honest statement is that the black hole star is now the leading explanation for the class, supported by the best data so far and not yet a closed case. The third misunderstanding is that black hole stars, if real, are around today, that you might find one in our galaxy. They are not. Black hole stars are creatures of the very early universe, requiring the pristine, heavy element-free gas clouds that existed only at the cosmic dawn. In the modern universe, gas is polluted with heavy elements from generations of stellar death, and that pollution changes how clouds collapse, fragmenting them into ordinary stars rather than letting them fall together into a single monstrous object. Black hole stars were a phase, a feature of the universe's youth, long since ended. The ones we're seeing are all in the deep past, their light only now arriving. The fourth misunderstanding is that the red dots breaking cosmology meant our science was simply wrong, that the whole edifice was crumbling. This is the opposite of what happened, and it is worth saying clearly. The red dots look like they broke the model only under one assumption, that their light came from stars. The moment a better explanation arrived, the black hole star, the crisis dissolved, and the standard picture of cosmic structure survived intact. This was not science breaking. It was science working, a strange observation, a period of genuine confusion, competing ideas, and finally a sharper measurement pointing toward a resolution. The headlines about broken physics were the sound of the process running, not the sound of it failing. No one expects a crisis in cosmology to resolve so cleanly into a stranger but stable picture. But that is what appears to be happening with the red dots. No one predicts that the objects which seem to break the universe would end up confirming an older theory and healing an older wound. And absolutely no one anticipates how often the word crisis in science really means we're about to learn something, rather than we have gotten everything wrong. So let us gather the whole journey now, gently, the way you would draw the threads of a long story together before sleep. We began with the little red dots, thousands of tiny crimson smudges scattered by the James Webb Space Telescope across the first billion years of cosmic time, each one a small contradiction. We found that they fit neither of the two obvious explanations. They were too bright and compact to be ordinary galaxies of stars demanding impossible numbers of suns assembled impossibly fast, the objects that had people saying Webb broke cosmology. But they also lack the clear violent signatures of ordinary feeding black holes. They sat in the gap between the only two answers anyone had, refusing both for 3 years. And then we walk through the third door, an idea decades old and almost never taken seriously, the black hole star. An object that looks star-like on the outside, a vast glowing envelope of gas, but that hides a black hole where its heart should be, feeding on the envelope from within, its light the glow of matter falling into the dark. We saw how a single object, glimpse 77.5, magnified by the gravity of an entire galaxy cluster and stared at for the equivalent of 80 hours, gave up the most detailed spectrum ever read from a red dot, and how that spectrum matched the black hole star line by line, the iron forests, the reprocessed light, the gas-made Balmer break, the feeding black hole wrapped in its dense glowing shell, and we saw how much fell into place the moment we accepted it. The universe-breaking galaxies stopped breaking the universe, because their light was never mostly starlight. The ancient seed problem found its answer, because a black hole star is the perfect sheltered incubator for growing a black hole fast. The little red dots turned out, very possibly, to be the cradles of the supermassive giants, the hearts of darkness wrapped in red fire where the universe grew its monsters. Before we get started on what comes next, it is worth knowing that this story is not finished, that what we have tonight is the strongest clue rather than the final verdict, and that the next few years are likely to settle the matter one way or another. Tonight we're going to look at how astronomers plan to confirm or complicate the black hole star picture, because the path forward is as interesting as the discovery itself. The single most important thing astronomers need is more spectra like the one from glimpse 1.5. That object was special because gravitational lensing magnified it enough to gather an extraordinarily detailed spectrum. One such spectrum is a powerful clue. A dozen would be a pattern. 100 would be close to proof. So the work ahead is, in large part, the patient gathering of detailed spectra from many more little red dots, especially those that happen to sit behind galaxy clusters, and so can be magnified the same way. Each one tested for the same fingerprints, the iron forest, the gas-made Balmer break, the buried feeding black hole. If most of them show the same signature, the black hole star interpretation will harden from leading idea into established fact. If they turn out to be a mix, that too will be a real and important finding, telling us the red dots are several kinds of object wearing the same color. There are other lines of attack. Astronomers will watch the red dots for variability, for changes in their brightness over time, because a feeding black hole tends to flicker as its meal fluctuates, while a galaxy of stars holds steady. They will look harder in X-rays, with the most sensitive instruments available, to understand why these objects are so oddly quiet in that light, which the dense envelope of a black hole star would naturally explain. They will refine the theoretical models, running detailed simulations of how a black hole star forms, glows and dies, and comparing the predicted spectra in fine detail to what Webb actually sees. And they will keep surveying, pushing the count of red dots higher and mapping how they are distributed across cosmic time, watching for when they appear and when they fade. There are real open questions that honest astronomers will tell you remain unresolved. We do not yet know for certain that all or even most red dots are black hole stars. We do not fully understand the conditions that allow a black hole star to form, the exact recipe of pristine gas and radiation required. We do not know precisely how the objects end, or how cleanly they hand off their grown black holes to the galaxies that form around them. These are not signs that the idea is wrong. They are the ordinary frontier of a discovery still being worked out. The questions that the next decade of Webb observations and theoretical work will steadily answer. What is genuinely thrilling is the pace. This is not ancient settled science. The red dots were discovered in 2022, became a crisis by 2024, and received their strongest possible explanation in June of 2026, days before we sat down together tonight. We are living through the resolution of this mystery in real time, watching a piece of the universe's history get rewritten as it happens. The picture may shift again, new spectra may complicate it, But right now, tonight, we are about as close to the answer as anyone has ever been, holding the freshest clue the cosmic dawn has offered. No one expects to witness a major cosmological mystery being solved in real time, over the span of a few years, but that is precisely where we are with the red dots. No one predicts which of the open questions will resolve cleanly and which will deepen, and the only way to find out is to keep gathering the faint light. And absolutely no one anticipates how alive this science is right now, how the very newest observations are reshaping our picture of the universe's first billion years, even as we speak, with the best instrument ever built still staring into the dark, gathering the next clue. No one expects 1,000 impossible things to resolve into a single quiet answer, but that is the gift the cosmic dawn just gave us. No one predicts that the strangest explanation, the one that lived for decades only in the margins, would be the one the universe had been holding up to us all along, written in red light. And absolutely no one anticipates how gentle the final picture feels once the alarm of broken physics fades, how the early universe turns out not to be broken at all, just stranger and more inventive than our textbooks were ready for. By the end of tonight, you're going to understand a pattern worth noticing, because the little red dots are not the first time the James Webb Space Telescope has been said to break cosmology, and understanding the pattern is genuinely reassuring. Almost from the moment Webb opened its eye, the headlines began. Webb finds galaxies too big to exist. Webb breaks the Big Bang. Webb overturns cosmology. Again and again, the telescope returned observations that seemed, at first, to shatter the standard picture of the universe. And again, the news travelled the world dressed in the language of crisis. The early massive galaxies that seemed impossibly large. The galaxies that seemed to have formed impossibly early. And now, the little red dots. Each one arrived as a potential earthquake. A sign that perhaps our whole understanding of cosmic history was wrong. And here is the pattern worth holding. In case after case, as more data came in and the dust settled, the crisis resolved, not by overturning cosmology, but by deepening our understanding within it. The galaxies that seemed too big were often measured more carefully and found to be smaller than the first alarming estimates, or their light was found to come partly from feeding black holes rather than from impossible mountains of stars, which is exactly the red dot story. The standard model of the universe, the broad framework of the Big Bang and cosmic expansion and gradual structure formation, has bent and stretched and absorbed each shock, and so far it has not broken. It has grown richer, stranger, more detailed, but its foundations have held. This is not because cosmologists are stubborn, refusing to give up a cherished theory. It is because the standard model is supported by an enormous web of independent evidence. The afterglow of the Big Bang, the abundances of the light elements, the expansion of the universe, the large-scale structure of galaxies, all of it fitting together with remarkable precision. A single surprising observation, however dramatic, has to be weighed against that entire web, and usually, when the surprise is understood properly, it turns out to fit into the web after all, in a place no one had thought to look, the way the red dots fit once we understood them as black hole stars. The framework is hard to break precisely because it rests on so much. There is a lesson in this about how to read the news of science, and it is a calming one. When you see a headline announcing that some new observation has broken physics or overturned everything we know, the honest translation is almost always gentler. It usually means we have found something we do not yet understand, and the process of understanding it is about to teach us something new. The breaking is rarely real. The learning always is. The little red dots look like a break for 3 years, and they turned out to be a doorway, leading not to the ruins of cosmology but to a deeper and stranger chamber within it. The black hole stars, the seeds, the dark hearts of the cosmic dawn. No one expects the repeated announcements of broken physics to keep resolving, quietly, into deeper understanding, but that is the actual track record of the Webb era. No one predicts that the crises would so reliably become chapters, the shocks so reliably become discoveries, and absolutely no one anticipates how steady the Great Framework turns out to be, how it absorbs one earthquake after another and stands, not because we cling to it, but because the universe, examined closely, keeps confirming that it was broadly right all along and only ever incomplete in its details. There is a quiet comfort in that, I think, and it is the thought I want to leave you with. For 3 years the red dots looked like a crisis, like evidence that we had gotten the universe badly wrong, and the resolution, when it came, was not that the universe was broken, but that it was building something we had not imagined, patiently, in the dark, 13 billion years ago. The fear was in our incomplete picture, never in the cosmos itself. The universe was never breaking. It was only doing something we had not yet learned to see, and tonight perhaps we have begun to see it. Far away and long ago, in the first billion years after the Big Bang, the dark was already at work. In thousands of small bright objects scattered through the young cosmos, black holes sat cradled in vast shells of glowing gas, feeding quietly, growing in secret, each one a star with a shadow for a heart. Their light has been travelling toward us for 13 billion years, and it arrived, at last, as a scatter of little red dots, and we have only just learned to read what it was trying to tell us. The red dots are glowing, far off in the deep past. The black holes are feeding, hidden in their shells. The universe is building its giants in the dark, exactly as it has since the cosmic dawn, patiently, without haste, without sound. And you are here, at the other end of all that ancient light, warm and still and safe at the end of a long day. Sleep well tonight. Good night.